Hi all. Seems we're waiting for the other participants to join. Hi Rohit.
So,
Give me 2 minutes. I'll share my screen. I think started now. So let me just share my screen. So study in education. I believe this is the one. Yep. So right. So I hope you can see my screen, right?
yes,
Yeah. Okay. So just to quickly recap, yesterday we were talking about a very common problem by the end of the session is that the problem we were talking about was multicollinearity. Yeah. So multicollinearity is where we saw that there may well be an interdependence. Okay. There may be an interdependence of uh, the features amongst each other, right? Which we need to get rid of. Now, something that I am not entirely able to remember whether I had explained this or not. So we looked into the function or the variable VIF itself or variation inflation factor, right? So we have also defined that it determines the strength of, let's say, correlation between the independent variables, because we thought they are independent variables, but now we might see they are not, right? So that's what we are trying to find out. It is predicted, or it is estimated, the value of this VIF is estimated by taking a variable and regressing it against every other variable, right? That's what we saw in the example. We took TV and radio and we tried to figure out if there is a relationship. And in the scatter plots that is actually loading as we speak now. Let me just see if it has loaded now. Yeah. So in the scatter plots, if you remember, we were looking into this relationship specifically, where there was some form of linear relationship between newspaper and radio, right? So there was some linear relationship here. Everything else was really scattered, and there was really no relationship. There may be somewhat relationship between radio and newspaper in the reversed order as well, right? So even if we change the axis, we were able to see some relationships. Now, if we have, let's say in this case, if we have already seen this, right? I mean, we have already seen this now, that, or we have already defined this now, that if we are able to get hold of such an information, we should be getting rid of the variables, unless and until the multicollinearity factor, in this case we are considering VIF. And there is one more method as well, which is kind of a difficult one. I'll not say it's a difficult one, it's a kind of an iterative one, but we will look into that one as well. It's called recursive feature elimination. But before we go in there, let's try to finish VIF with some code, and then we'll go in there. So if we are already looking into this correlation matrix or the heat map that we have seen, then why? I mean, why do I really need to? If I have already looked into all these values over here, all these graphs over here, then do I really need to look into any other factor like VI, right? So one of the main reasons how we can explain or how we can justify our action is that although there is a correlation matrix and although there are a set of scatter plots which are useful to find the multicollinearity problem, these findings only help show us the bivariate relationship between independent variables, right? Now, VIF is preferred because of a very simple reason. It is preferred as, or it is preferred because it can show the correlation of variable within a group of other variables as well, right? So that's exactly what we are going to do. Now, this is a bit difficult or a bit tricky to understand at the first place because we have not seen it in action yet. So let's just try to find out. Let's just try to do some analysis here. So I'll say applying uh, VIF. Okay, but before even applying that, let's do one thing. Let's try to properly write this down, and I'll first of all say rechecking the columns list of my data once more. Yeah, so I'm going to say advertising dot columns, and I get a list which is like this. Now I'll take this list, and then I'm going to say let's create a list of features. Okay, so I'm going to define a variable called features. And I'm going to take, let's say, TV, radio, newspaper. Sales I don't need. Scale I have already converted to is large, so I'm getting rid of that. Is large SK, I'll get rid of that because I just need one of them, right? I don't need two of them. Targeted geography, I can get rid of that because this was a textual column and I've already converted that into, one hot encoding that we have done. We have converted it into targeted geography, suburban and urban columns, right? So I can consider these 1, 2, 3, 4, 5, 6 fields as my features, right? Now, as of now, we are only interested to look into what is happening within the features. So there is no point of defining the target, but we can also define that. But let's now select the data, right? Let's now select the data basis the features columns that we have defined above, right? So what I mean by that is let's create a variable called X and I'm going to say advertising, X is equal to advertising, and in brackets, I'm going to say features, right? So what this means is now I have a variable X, which is basically the data set with only the features. Okay, it is the entire thing. As you can see, I have six columns because I selected 6 features and 200 rows. So it means I've taken the entire data and I've only selected or filtered it on the basis of the features that I've already written over here, right? So why I've done that is because this makes my life easy. Okay, so I'm just going to say checking the features data, I can say. Yeah. So this is going to make my life easy when I'm going to apply VIF. So let me just create a few more lines over here. And now I'll say let's apply VIF using stats models library. Okay. So when we are going to apply stats models, there is a function or there is a module in stats models first, which is called outliers influence, right? It is present in the module called stats. So you can say that outliers influence is a sub module of the module stats, which is available under the stats model library. And in there is a function. There is a function which is already created, and that function is called variance inflation factor. Okay, so I'm simply going to use that function. It is already created for us, and then I don't have to do the calculations by hand, right? So but if I have to use that, I'll have to import the library, right? So let's just save the notebook and go back on top, because we decided, right, that we are going to define all the libraries over here. So what I'm going to say over here is from stats models dot stats dot outlier outliers influence. Okay, from stats models dot stats dot outliers influence, import variance inflation factor, right? So this is used to calculate the VIF, right? So this is what I'm going to use. I believe I have written the name correctly. Let me just execute this, and obviously there will be an error if it is wrong. But fortunately, I did not get any error. You see, it is executed now. So it's good. So we have imported the function that I need. So let's just try to see what I'm going to do. So there are a few steps, so please pay just a small amount of attention. Okay, so what sorry for that. So what I'm going to do is that I'm just going to create a data frame where I'm going to hold the output. I'm going to name that as VIF only, because obviously we're looking at VIF. So to make things simple, I'm going to say that it is a pandas data frame. So I'm creating a data frame to store my final output containing the VIF of my features. Okay, so this is the data frame that I'm going to make use of, right? So let's go on to the next stage. So what we are going to do now is that I have X where I have the columns, right? So what I'm going to say is that let's create a column, okay, in the VIF data frame, which will contain the feature names, right? So I'm going to say VIF, and then the column name can be called as, oh sorry, the column name can be called as features. Okay, features is equal to, I already know the list of features, so I can either do x dot columns, or I can take the features from my features list, right? I have already taken the features list, so I could have said features as well, or uh, features features variable can also be used, right? So that also I could have done, right? So it is both the same thing. Now I have to calculate. So when I calculate, what I'm going to do, I'm going to use a 3-step process. Let me just write it down and then I'm going to code it. So the process to find VIF will be step number 1. I will calculate the VIF for, okay, each feature, right, that I've already selected. Then what I'm going to do, I will round the VIF values, okay, to 2 places of decimal. This is an optional step to do. Optional step. I'm doing it so that I can read it properly. If I have a lot of numbers behind the decimals, it becomes very cumbersome at times for me to look at the numbers and come to a conclusion which is greater than, or which is less than, or which is a better value, which is a smaller value, and so on. So that's kind of a limitation from my side. So that's why I actually prefer doing it to 2 places. If you're okay, you can leave it, right? But the third and the most important thing, finally, the third and the most important thing is I will sort the final output. The final output will be stored where? A VIF data frame, right? Right. I'm going to sort the final output, okay, by the VIF value in the descending order. Okay, so basically what I'm expecting to find is something like this. I am going to find a table, okay, a table that looks like this, and in this table there will be 2 columns. So this will be the data frame VIF. Okay, this is the data frame that I'm trying to explain over here. Here the first column will be features, the first column is going to be features, all the list of the features. So there will be TV, radio, so on and so forth. And then in the second column, I'm going to add a new column there called VIF. Here, I'm going to write the values. Okay, and then I'm going to sort it in the descending order, right? Then I can get the list for each feature, what is the variance insulation factor, which this feature is adding into the set of features or into the data set. And accordingly, I'm going to say if this value is greater than or equal to 10. If you remember the thumb rule that we discussed yesterday, if this value is greater than or equal to 10, or for that matter, any value is, right? Because I have sorted it into the descending order, it makes my life easy. So I'm going to look at the first value and say, okay, if this feature has a VIF which is less than or equal to 10, I'm going to get rid of this. All right. Basis, I have a mathematical intuition now, which is VIF, as well as there must be a business intuition behind this as well, right? If it is a very important feature, then the answer is no. I cannot get rid of it. I cannot get rid of it out of my model, because my model at the final stage, the final outcome of the model is something that I can use in the real world. If I'm getting rid of things that I control, I really like, or my business is really dependent about, then there will be a problem, right? So that's why I cannot get rid of this. If not, then I will get rid of the next variable and so on. If at all the value of VIF is greater than or equal to 10. right? Which we are going to find out. So we don't know what this value is going to be, right? So let's try to calculate the VIF value first, and then we are going to go ahead, right? So VIF is the data frame name, and here I'm defining a new column called VIF. This VIF column is going to have the values. Okay, so the values will be in form of a series or in form of a list. Hence, I have defined it into this kind of bracket. Right. What I'm going to write is now a one-liner function. Okay, kind of a lambda function, kind of an iterator, which we have already seen when we looked into the basics of Python. Right. So what we are going to do is we are going to call this function called variance inflation factor, and I want to calculate the variance inflation factor for something, right? I want to calculate it for something. Okay, for what will that be? I'm going to write a loop over here. So this is a single liner loop concept that I'm using. For I in the range, I is my iterator variable here. So for I in the range, x dot shape, okay, x dot shape, and I'm going to take the output as 1. So let's try to see what this is doing. If I do x dot shape 1, I could see what is the value. It is 6. So I'm going to take for I in the range, 6. So for 6 times you go on and you calculate the VIF for x dot values. Okay, what is x dot values? If I take x dot values and come over here, and these are the values. So you take the values, right? You take the values and then you calculate the variance inflation factor for each I, or for each position of I, or for each iteration of my data, right? If I do that, I get the VIF. But then obviously my second step is I have to convert this, right? I have to round this. So how do I do that? There is already a function. There's already a function in Python which is round. So I want to round it to 2 places of decimal. So I'm going to take this value over here. Just a moment. I'll just do a copy paste so that I can save some time. And I'll take this value, round it to 2, and put it back into this value, right? As simple as it sounds. Now what I'm going to do, final step, I'm going to do a VIF is equal to VIF dot sort. Okay, I want to sort by means of values. Okay, hence the function name is sort values. I want to sort it by the values which is found in the column VIF, right? And the type will be descending, hence the variable or the feature ascending will be set to false, right? So this is the construct, the way in which you use the function sort values, where it takes 2 parameters. By is the column name by which you want to sort this data frame, which in this case is my VIF value. And then I mentioned ascending is equal to false. By default, ascending is equal to true. So by default, it's going to do it in the ascending order. I don't want that, right? I've already written, I will sort the final output, the VIF data frame, by the VIF value in the descending order, right? So that's exactly what we have done over here. And now the VIF data frame, if I have done things in the right way, then it should be ready. So finally, let's see the VIF values. Okay, let's quickly revise, or let's quickly cross check if my code is correct. So what I'm trying to do, I have taken this list of features with the features that I have selected, getting rid of what I have already converted or the unwanted ones, and then I have taken an X series or an X data frame. Actually, X is a data frame here, which is a subset of advertising data frame of the features only. Then I've checked the value of X, which is looking good. It only has the features. There is no sales or any other variable which I don't need. Then I've created a new data frame named VIF. Here I'm going to store the output. I'm going to create a new column called features, which is the columns. I could have also used this list of features as well, which is the one and same thing. Then to calculate VIF, I added a new column in the same data frame named VIF. There I have done this inline calculation, single liner function, where I have said, call the function variance inflation factor, apply it on x dot values for each iterator value I, where I will iterate in the range of 0 to 6, right? So this is how we can specify it. X dot shape 1 is going to define the number of columns which we have. If I do x dot shape, I'm going to get the output as the number of rows, and the columns I'm selecting 1, which is basically the number of columns, right? So that is exactly what I've done over here, right? Let's see if this has worked or not. The answer is yes. It seems it has worked. It has not given any errors, and I have got the variance inflation factor. Okay, look at what is happening over here. These are each and every feature which I have in the data, and this variance inflation factor, okay, is this feature's effect on the rest of the features. Okay, so if this value is higher and higher and higher, then I can say that this variable is actually affecting, or it is dragging the rest of the variables, right? Here in this case, I could see for the first two variables, the value is almost the same, right? The value is almost the same. This is also a good indication. If even the third value, but none of the values, okay, none of the values are actually greater than or equal to 10. Is there any value like this? The answer is no, right? So we are not facing, as per VIF, we are not facing any multicollinearity problem, right? Uh, just a moment. We can actually create we can actually create our model with all these variables, okay, and then we can find out, we can actually create our model with all these variables. This is what this process is implying, and then we can try to optimize. Optimization is something which we have already done earlier, but this is like we are doing some kind of a reverse engineering here, that we are trying to figure out the best variables. Just we are trying to, in this case, in case of VIF, we are trying to get rid of the bad variables, the variables which are going to, or which might be dragging my value. So let's say in this case, if this value was not 3.38, it was, let's say, 13.38, okay, then I could have clearly said that the variable TV having a variance inflation factor of 13.38 is by this terms inflating, okay, inflating the variance in my data and affecting the rest of the variables. It is time to get rid of it. Now, can I really get rid of that? If not, then I'll have to rethink and about the rest of the variables which I have, right? Now, the other thing that we have to note over here, if there are more than one variables with exactly the same variance inflation factor, okay, there is nothing to worry about. It simply means one very simple thing. It simply means you can either create a model with TV, or you can create a model with radio, or we can create a model with both. So it can either be a simple linear regression with any one of these two variables, or it can be a multiple linear regression with both of these variables. In both of the cases, our model will not be entirely reliable. Our model will not be entirely unreliable, right? So we are not going to get any bad model out of this, right? So that's what we can write over here. Let's write our findings. Our findings are, okay, none of the features we see in the data has VIF value, okay, which is greater than or equal to 10. Hence, we do not have a multicollinearity problem, right? We don't have a multicollinearity problem in this case. Hence, we do not need to ideally remove any of the features from the data, right? However, however, basis our earlier findings, we can choose or decide, okay, which features will be present in my final model. Okay, this selection I'm going to do basis some very easy things, right? This decision can we have already made earlier using very simple things like r squared, right? R squared value and p value, or its combination, right? So this is what we have exactly done earlier. We have already found the models. This is like we are trying to improve the model, and we are trying to see if we have done anything wrong that we need to get rid of, or if we have not done things in the right way that we need to get rid of, and so on, right? So this is what we are exactly doing. Just a moment. Okay. Now, this is one of the ways, okay? One of the ways in which we have looked into variance inflation factor, okay? This is one of the ways in which we have looked into variance inflation factor. There is one more way, as I said, there is one more way, and there is one another. I will call it a tedious way. Okay, I am going to call it a tedious way, although the kind of data that we have, right, it is really not a very tedious thing, because we really have a very small kind of a data. If you look at our final feature list as well, it is only 6 features, right, which we have. So it's not really a very problematic thing to do. So maybe we can try it over here. But our what we are going to try now, otherwise known as uh, uh, just a moment. Give me one. Yeah. What we are going to do now is a technique known as RFE. And RFE, what it does is it is a recursive way. Okay, it is a recursive way to eliminate. Okay, it is a recursive way to eliminate the features. Right, it is just a recursive way to eliminate the features. Okay, that's exactly what I'm going to do. So to do this, there are multiple ways. Obviously, every library, there are multitude of libraries in Python which can do this. But what I'm going to do, right, is that I'm going to import sklearn. Again, I'm going to get back to sklearn, because in sklearn there is a feature selection a module, and inside that module we already have a function, we already have a method, a class called RFE, whose methods can be called, and then I can do this very, very easily. Right, I can really do this very, very easily. Okay, and that's exactly what I'm going to do now. So to do that, uh, so what I can say over here is that let's also, for our sanity purposes, check the findings from RFE. Okay. Now, what RFE or how RFE differs, okay, from VIF is that it also helps. It also helps. This is the punchline. Okay. So it also helps to identify on a very crude level, okay, basis the VIF, the most important features which are actually, okay, responsible responsible for the variation, or I'll not say variation, responsible for the explanation of the variation within my data. Right, so what I mean by this is, let's just copy this. This is RFE. I'm sorry for the spelling mistake. So let me just copy this and let me put it into my notes as well, so that it is there. So 38, point number 38, I'm going to write another good method to undermine, okay, the effect of multi-collinearity problem, okay, is to use recursive feature elimination, or RFE. Okay, and then I'm going to paste this. How RFE differs from VIF is that it also helps to identify on a very crude level the most important features which are actually responsible for the explanation of the variation within my data. Right, that is uh, it helps identify, okay, I'll not say properly, I'll say to a good extent. Okay, not really a very extensive kind of a method, and you will come to know why it is not. Maybe in this data set we wouldn't come to know, but there are other data sets where it would have been evident. But in this case I'll explain. Okay, I will try my level best to explain what is the problem with this RFE method, because the answer is there in the name itself. It is a recursive way of doing things, right? We are going to get an output out of RFE, and from that output we will look at something, then we are going to take another decision. We will remove a feature, then we will take another call. We will remove a feature, take another call. This kind of a recursive activity is going to continue until unless we get a list of features which are actually contributing to the estimation of my final value, right? So that's exactly what is the problem with RFE. I hope you have understood what is the main issue here. If you try to relate this to any real life or any practical use case where you have a lot of features, it is really difficult to use RFE and to manage that, right? In a production pipeline, this is really going to be a very, very difficult thing to do. But it helps. It helps to identify to a very good extent what features will really add value to my model, right? This is something that it does. right? So let's try it. Let's see if it is really doing it or not. But for doing RFE, of course, as I said, I need I need a module. So I'm going to say from sklearn feature, was it feature selection? Yeah, it was feature selection. Yeah, import RFE, right? This is used to perform recursive feature elimination. Okay, I'm just going to execute this. Let me see. No, there is no error. Good. I'll go back and I'm going to say, let's apply RFE. Okay. So what I'm going to do over here, I'm going to apply RFE by a very, very simple mean. And to do that, before I even do that, let me just do one thing. Let me just also create, there is a chat, I believe. Can there still be multicollinearity even if VIF is less than 10? Yes, the answer is yes. Yes, Sarangs, the answer is yes. There can be multicollinearity if VIF is less than 10, but it actually depends. Okay, it depends whether you are going to handle that or not. Multicollinearity is always there. Okay, multicollinearity is something which you cannot reduce, which you cannot convert to zero. That is a misnomer. You can never get rid of multicollinearity. Multicollinearity was from the first moment you started generating this data, because every variable is somehow related to the other variable, right? Somehow, practically or impractically, mathematically, or from a business point of view, it is always multicollinear. However, if it is more than 10, right, why are we choosing this as a benchmark? Is that if it is more than 10, then it is obviously that the feature is obviously a problematic feature which is causing the other features to get affected because of itself, right? It's like choosing the best student in the class, right? You can't say that a person who has got 73% or 77% is not a good student, right? But if you look at the overall scores obtained in math or in science in that class, and if you see there is a student who has got 97, obviously that student is one of the best, right? You can close your eyes and say that the student is the best, right? And that's why we are taking a kind of a cutoff. So that's what, even when during the admissions into the colleges, we also do, right? The cutoff of having admitted in statistics and so on, so college is going to be 85% in your class 10 and class 12, right? So why do we do that? Is it an indication that 80% or the person who has got 80% is not a good student? No, it's a cutoff to ensure that I am getting the best of the best, right? I'm actually getting people who are really very good. Exactly, that is what is actually happening here. So taking a VIF of greater than 10 or greater than or equal to 10, right? It is not greater than 10. Greater than or equal to 10 is just a benchmark, right? It is just a benchmark. Now, even this next statement is going to confuse both of you even more. Just because there is a VIF of greater than 10, there may well be a data scientist in a certain scenario who will not get rid of any variables, right? Because irrespective of the fact that there is VIF, the data scientist will humbly say, I accept there is VIF, but there is nothing I can do because I have selected 5 features or 4 features which are very, very critical to my business. I control all of them, and it is impossible for me to go back to my business and convince them that I should not be concentrating on feature X1 as opposed to feature X2, X3, and X4, right? All of the features must be controlled, must be accessed, or they must be tuned, right? Or they must be considered as part of the model, right? So before we go in there, we have already created list of features, right? So let's firstly create the series for output or target variable. I'm going to call this Y, and Y is going to be advertising sales, right? Now I can apply RFE easily. Okay, X and Y I have taken, and why I have done this is because I am going to apply a linear regression model. So this is one thing about RFE that we need to know. Okay, RFE, I'm going to write it over here, 39. RFE, recursive feature elimination, can only be actuated, I can say actuated, once or if we have actually fit the model. In case of VIF, this was not required, right? When we were looking at VIF, did we create the model? No, we only looked at the features and we decided what is going on over here. But in case of RFE, you have to fit the model. Okay, so to do that, I'm going to create a linear model variable, LMRFE. Okay, LMRFE, or maybe the naming convention that we were using. Let me just quickly check what we were using. Give me 1 minute. I think we were using this one, right? Right. So I'll come down. SM was for stats model. I'm not going to use that. So in this case, so what I'm going to say, this is what, okay, I'm just going to call this like SKL. Okay, multiple linear regression using scikit-learn in conjunction to RFE. I'm going to create this as an object of linear regression class. Okay, I have to fit the model. There is no other way I can survive, right? I have to fit a model. So I am saying create an object of linear regression model to be fit later on using RFE. Okay, now I have to apply RFE here, and before I do that, I have to fit the model. Let's fit the model first. So to fit the model, what I'm going to say, MLR SKL underscore RFE dot fit, and I'm going to use both X comma Y. It's a very bad thing that I've done over here. Ideally, I should have broken this into testing set, training set, and I should have done that, right? But we have a very small kind of a data set, and here I just want to explain you what is the usage of RFE. That's why I'm not doing it. Ideal condition, please always do it. Break X and Y into X train, X test, Y train, Y test using train test split function. You may or may not want to use random state. That is up to you. It doesn't really matter. Please decide the training side and the size of the training data, the size of the testing data. Pass the values X and Y, and you will get the output. Right now, let's uh, perform recursive feature elimination. So I'm going to call this variable as RFE just to make my life simple. And I'm going to call that function RFE, which I've just imported, where I'm going to pass this model, which I've already fit, and it contains my model, let's say parameters. And I'm going to say, I have how many features? 6 features. Let's consider all the 6 features. The second variable actually determines how many features I'm actually going to consider. Okay, how many features am I actually going to consider? We are going to see what is the effect of changing that value. Okay, but we cannot go beyond 6, right? It may or may not give us any errors, but it does not make any sense, right? Now, final step, RFE is equal to RFE dot fit. I have to fit this RFE object as well with my X and Y data. Now I have got the RFE, and I would like to, let's finally I will check the, just a moment, finally check the outcome of RFE that we have performed. To do this, I'm going to use 2 functions. I'm going to use a list function, and I'm going to use a zip function. This is the first time we are looking at zip function. So let me explain what zip function does. Okay, what zip function does in case of this programming language that we are using. The zip function is where I'm going to pass multiple values. Okay, I'm going to pass multiple values, and it is going to create a set out of those values. What I mean by this is the first value I'm going to pass is x dot columns. I'm going to pass the name of the columns, or I could have passed the variable features. Then from this RFE object, I'm going to pass a variable called support. Okay, we are going to look into what is support and the other variable known as the ranking, but I'm going to pass these values as of now into this zip function, and what it is going to output me is something like this. For each and every feature, I'm going to get a set which is like this. It is just going to zip my set. I don't have to write any for loop, while loop, or any kind of looping construct. It is just going to zip it, and each and every set will become one row for me as an output of this zip command, where the first column, okay, the first column will be x dot column. So it is going to take the column name C1. In the second place, it is going to put the value of support, comma, and then in the third case, just a moment. Yeah. And in the third column, In the third column, it is going to take the RFE ranking output and it is going to put it over here. So that's exactly what zip is doing. Okay, now just to make it look better, I may want to convert this into a list. Okay, then I can look at it in a better way. That's all. Just for the look and feel, I'm going to also apply a list function on top of this so that I can look into it in a better way. Let's see what is the output. Look at the interesting thing which is happening over here. The first column is talking about the features. The second column is always true. Why? RFE.support underscore talks whether this variable or this feature TV is really having the support from this RFE activity that we have done. In other words, RFE supports this variable, okay, to be part of your final model or no. The answer for each and every variable is true, right? Why is this the case that for all the 6 features it is true? Is because I have taken this number as 6. I have not given it any benchmark, right? I have not given it any benchmark like VIF. In case of VIF, we said anything greater than or equal to 10, it is a bad thing. It is doing something wrong for me. Fine. Let's give it some value over here. Let's say 3. If I give 3, now see what is happening. Okay, now see what is happening. Now it is telling me which variables are actually adding more value without the problem of overfitting. We are going to discuss overfitting in great depth in the next session. We wanted to do that in the last session as well, but we could not because of whatsoever reason. But why, if I select 3 or if I select, let's say 1, okay, how it is going to work is that it's going to select that one feature which does not have any multicollinearity problem. This may or may not relate sometimes to your business problem. See what is the problem here. If you take so less value as 1, the output is being given as targeted geography R1. Why is this the case? Why do you think it is the case? Why, if I convert this 1 to 2, what do you think is going to happen? Is it going to consider TV variable? It will not. You see what it has done. It has taken into consideration is large and targeted geography urban. Any guesses why this is the case? Why is RFE, when I'm giving it a value of 2, it is selecting variables like is large and targeted geography urban, which is already encoded? Okay, the answer to this question is it is taking these values because they are encoded and hence they are normally distributed. Because they are already normally distributed, this RFE is getting dragged towards them. It is under this impression that why should I select TV or radio or newspaper if I have normally distributed variables like this? Okay, change this to 3, see what happens. Okay, change this to 3. Now it has started to consider the other variable. Okay, it has an algorithm that is running behind it. Okay, you can read into it in depth, but choosing a very less value is actually a problem. You should always choose the right list of features, or you should take all the features over here. That is what I did exactly at the first place. And you see what is happening. Then you reduce this from 6 to 5, and then you see what is happening. If I reduce this to 6 to 5, you see what is happening. Everything in the third column, this is the ranking. Okay, if you look at the ranking tells which is the most important and which is the next important. So most important list contains TV, radio, is large, targeted, and targeted. Why are these 3 considered? Obviously, because RFE is getting dragged. RFE is getting I can say influenced by the fact that those 3 variables are encoded and hence they are lying in the normal range, right? They are within the range of 0 to 1, very properly normally distributed. That is why it is getting diverted, right? But at least something that it has correctly done, which we have already seen using stats model as well, which is this. Newspaper was adding a minus coefficient to our equation, if you remember. It was negatively impacting the sales of my items, and that's exactly what it has done. If I take this list as final, I will not use newspaper in my model, right? So this is exactly what RFE is asking you to do. If there is any ranking which is equal to 1, you take those 1 ranking first and create a model. Then if that model is not good or not usable, then you take 1 and 2. If also in that case it is not usable, then you take 1, 2 and 3 and so on. This is the way to progress with RFE. That is why it is a cumbersome process. Right? This was not the case in VIF. VIF was comparatively easy. We looked at VIF, we look into the VIF value greater than or equal to 10, I can get rid of that variable mathematically, right? Or influenced by my business decision, I may not even get rid of a single variable. That's a different problem, right? But in case of RFE, you see, I have to recursively do this. Let's try to change the 5 to 4 and see what it is going to do. If I do 4, now it is saying I don't need TV. Why? Because out of TV and the radio, it is selecting one variable for you. Why is that the case? Any idea? Go back, look at the VIF. This is exactly what I explained during calculation of VIF. VIF for TV is equal to VIF of radio. You can choose any one of them. Right? This is the testimony. RFE is actually interdependent on VIF. Somewhere within its algorithm, it is taking care of VIF. Right? It's referring to VIF. Obviously, it is referring to. Otherwise, it could have either chosen TV or it could have either chosen radio. Right? It could have chosen both, but it has not. We have already seen our model was very good when we chose TV and radio both. But in this case, it is choosing only one. Why? Because the variance inflation factor is actually the same for both TV as well as for radio. So that's why choosing only one will solve my problem. Right? Be very careful when you're using RFE. RFE comes with a lot of practice. RFE comes with practice as in the sense you apply RFE, you get an output, you create a model, you find the statistics after applying the model into production. Then you come to know whether your model is actually good or not. Your pre-assumptions that my R-squared value or my P values are good may even get proven wrong in the actual reality when the model goes into production and people from business start taking decisions basis your model. Please be very clear about your business, about your officials, that there will be changes. Okay, a model once put into production is not going to remain as it is for its lifetime into production. It is going to change. It is going to change basis how it behaves in the real world, and then only we get back and then we make changes in our sample, in our data, in the way the data was captured, in the way these calculations were done, and so on. Right? I hope I was able to explain you what is the meaning of VIF and how RFE is going to be used. This technically concludes our multiple linear regression as well. There is nothing more that we really need to look into when it comes to multiple linear regression. So what we are going to do, or what I'm going to do, is that I would like to share a data set with you. It's a data set which has some housing data in it. Okay, and as we may have briefly touched in one of our very early stages of the defining of the question, we had already said that there can be a situation where I would like to estimate, right, the price of the house. I would like to estimate the price of the house basis the factors which is affecting the house, like whether we have a road in front of the house or not. Right? So in our portal, I'm going to share you with the data that's with this housing data. I would like all of you to go through it, and please try to apply, right, as much as we have learned. I'll just write over here that this is the conclusion for our regression modeling. Okay, I will not write the last line. I'll just say end over here. Right? It is quite clear that we have understood that our model using TV and radio will do fine, or either of TV and radio will do fine as well. Okay, let's make it a stop here, friends. We will continue tomorrow. Thank you so much.
Thanks, Cormac.
Thank you.
Thank you.